A revolution is happening way faster than anyone thought, and it's forcing us to ask a really big question. Has the insane energy crisis caused by AI finally met its match with quantum computing?
And listen, this isn't some prediction for the distant future. This is the timeline we are on right now. A recent breakthrough is taking quantum computing from this theoretical maybe someday idea to a very real, whoa, it's here. And it's looking like it could solve one of the biggest roadblocks in all of tech.
Okay, so before we get to the amazing quantum solution, we really have to get our heads around the massive scale of the problem. AI is unbelievably powerful, but all that progress is coming at a cost that is just completely unsustainable.
Here's the bottom line. The path we're on with AI just isn't going to work long term. The more powerful our AI models get, the more energy they need. It's that simple. And we are coming up fast on a hard physical limit of what our power grids can actually handle. This chart right here shows you exactly what that wall looks like. Data centers, the backbone of all things AI, are on track to double their electricity use by 2030. That kind of growth just can't keep going. Something's got to give.
To make this real, just think about this. A single, powerful AI chip can use as much electricity as an entire house. Let that sink in. We are literally designing a future that needs an impossible amount of power to run.
But what if there was a totally different way to compute? I mean, one that's not just faster, but radically more efficient. Well, this is where quantum mechanics makes its grand entrance. So the quantum advantage really comes down to this core law of physics called Landauer's principle. And what it says is that every single time a normal computer erases a bit of information, setting it back to zero, it has to release a tiny bit of energy as heat. That warmth coming off your laptop right now, that's it. That's Landauer's principle in action. And when that happens billions of times a second, all that heat really adds up.
And here is the absolute game changer. Classical computers are just constantly throwing away energy as heat by erasing bits. But quantum computers, they're reversible. Instead of just deleting information, they can uncompute it. It's like running the calculation backward, and they can do it without that mandatory energy loss. The takeaway is simple. For the exact same problems, they can be exponentially more energy efficient. It's not even in the same league.
So quantum computing is the silver bullet, case closed, right? Well, not so fast. It turns out the solution isn't quite that simple. Not all quantum computers are built the same, which has kicked off this incredible, high-stakes race to build the right kind of machine.
And when you're talking about energy efficiency, the answer is a huge, definite no. The specific way you build your quantum computer matters a lot.
So let's look at the big players in this race. You've got Google, using these things called superconducting circuits. They're super fast, but they're also super fragile, and they need to be kept at temperatures colder than deep space. Then there's Microsoft, chasing this wild topological design, which in theory is more stable, but they haven't quite proven it yet. And then you have companies like IonQ, and they use individual atoms, trapped ions, which are just naturally stable and don't need all that crazy cooling. As you can imagine, each one has a totally different energy bill.
Now look at this number for a second. 25 kilowatts. That is a ton of power. But what's it for?
Get this. That's the power needed just for the giant refrigerators to keep Google's computer near absolute zero. Most of the energy isn't even for computing, it's for cooling. Meanwhile, other approaches, like the ones using trapped ions that run way closer to room temperature, can use 3 times less power for the same size processor. This is a huge deal. So why does any of this tech race actually matter? Because this isn't just about building faster computers. This is about building machines that can solve problems that are literally impossible for us to solve today.
And this is where it gets really mind-blowing. We're talking about being able to design hyper-efficient energy grids from the ground up, create revolutionary new batteries by designing them atom by atom, inventing totally new materials. And, crucially, this all comes full circle, feeding back into AI, giving us a path to make it not just more powerful, but finally, sustainable.
Which brings us right back to that urgent timeline from the beginning. This is not a problem for the 2030s. The choices being made right now are literally shaping the entire future of how we compute.
Remember these years? 2026, 2027, 2028. This is the window. This is when this technology is predicted to move out of the lab and into the real world. The race is on. AI's energy crisis is very real. And this just might be the solution we've been waiting for. So what's the prediction from the industry roadmaps? Here it is. By 2028, we will see the first large-scale quantum computers solving actual commercial problems that our best classical machines just can't handle. We're talking about a genuine phase shift in what humanity is capable of.
Okay, so what should you do about all this? Well, if you're an investor, you've got to focus on energy efficiency, not just raw speed. The most efficient tech is probably going to win this marathon. If you're a tech professional, you need to start learning these principles, like yesterday. The talent shortage is already a huge issue. And if you're a business leader, start asking yourself, what are the impossible problems in my industry? Because those are about to become your biggest quantum opportunities.
You see, we aren't just building faster machines anymore. We are building machines that work with the fundamental laws of physics itself. We are right on the edge of being able to master complexity in a way we've never been able to before. The age of quantum abundance is coming. The only real question left is, will you be ready for it?